going to speak for us about the period index problem for higher degree Galois cohomology groups over Hensel semi-global fields.
Thank you so much for the invitation and the introduction. My name is Yidi Wang from Western University, and today I'm going to be talking about the period index problem for higher degree Galois cohomology groups over Hensel semi-global fields. So my talk will be more of a algebra flavored, but I think this is also a problem like a lot of number theorists interested about, even though I'm working with a different kind of field. Yeah, so first, the outline of this talk will be first I'll introduce the classical period index problem and how it relates to this generalized one and my main result. Then I'll be introducing the main technique I used in proving my theorem, which is patching for arithmetic curves and also local global principles in Galois cohomology. And if you have time, I'll also be introducing a sketch of the proof. And also, this is actually the first time me giving an online talk of a slightly longer period. So I'll just pretend I have a blackboard. I'll just write while I'm talking. Yeah. So first, let's start with the motivation, which comes from the classical period index problem from the bar group. So if you start with a field F and a central simple algebra over F, so this is a central simple algebra is a finite dimensional associative algebra over the field F, which is simple. And also the center of this algebra is exactly the field F. For a central simple algebra, there always exists a finite field extension E over F. Such that when we base change this central simple algebra to the bigger field E, it splits into a matrix algebra. So we would also say A splits over E. Okay, so if we have two central simple algebras, from now on I'll use CSA for central simple algebras. So central simple algebras A and B are equivalent if there exists M and N, such that when we tensor up this A with a matrix algebra of size N, it's isomorphic to B tensor with this matrix algebra of size M. And we also say this a sort of Morita equivalence. Then once we define this equivalence relationship, we can define a bar group as the group of equivalence classes of central simple algebras over F. And one remark is that the bar group is torsion. And if we take the M torsion part of the bar group, it's isomorphic to H2F with coefficients mu M. Here, this mu M is the mth root of unity. Then then let's go to the elements in a bar group. So if we take a bar class alpha, we can define the index of alpha as the minimal degree of a field extension E over F such that alpha splits over E. So here, like by alpha splits, it's just saying the corresponding central simple algebra splits over E. And we also define the period of alpha as the order of alpha inside Brauer group. So if we have like a period of alpha is P, then we must have like HI alpha like stays in HI F like with H2 F with coefficient mu P. Yeah. So there is a fact actually just due to Brauer. So we know like period of alpha and the index of alpha has exactly the same prime factorization. So meaning we always have period of alpha divide like index of alpha, also divides period of alpha to the some power d, but this d depends on alpha. So then this will motivate the classical period index problem. So we may ask, does there exist a d such that we have like index of alpha divides period of alpha to the d for all like alpha inside the Brauer group? And if so, is there a bound for d? There are like some known results in the literature, and I'll like summarize a little bit. So when F is a global field, we always have period of alpha equals index of alpha. So meaning this case is d equals 1. And if we have like F is QP of T, this result is due to Saltman. So if we have P doesn't divide the period of alpha, we will have like index of alpha divides period of alpha squared, meaning this here the exponent d is 2. And when F is a function field, of 2 variables over a separably closed field, little k. So this result is due to de Young. So the result is saying if we have like characteristic of k doesn't divide period of alpha, we will have index of alpha equals period of alpha. And this is also the case when d equals 1. And another classes of fields, I want to say a little bit. It's like somehow like our focus, like the focus of this talk, when F is a semi-global field. So meaning it's a one variable function field over a complete discretely valued field. So if we say this complete discretely valued field has like a residue field small k, yeah, so when the characteristic of k is co-prime to period of alpha, I'm not gonna like state the like whole statement of the result of this like results, but I will be like giving some like examples to see what's going on there. And also this result is due to arbiter Hartmann question, also by Max Lieblich. Yeah, so the first case of a semi-global field which basically recovers Saltman's results is when F is a one-variable function field over QP. And in this case, when the characteristic of the residue field coprime to alpha, they also have index of alpha divides period of alpha squared. So here also d equals 2. And also in the equicharacteristic case, so if F is a like Laurent field of Laurent series over like C or like maybe other algebraically closed fields, and you take a one variable function field over that, you will have index of alpha divides period of alpha squared, which is also d equals 2. And another example, you can also like do this.
Sorry to interrupt you. In all these cases, so this D is there's a minimality condition. So the smallest D is 2. Like, do we know that the index and period are not the same in these cases, or they don't have to be the same?
I think here they do have proof this bound is a sharp bound.
I see. Okay.
Yeah. So like when the like dimension of the field gets bigger, I think it's impossible to have the case index equals period.
Thanks.
Yeah. And another case is you can also like making this complete discretely valid field of like higher rank. Then you can, for example, do like a field of Laurent series over QP, and then you have a one variable function field over that. And in this case, you have so like the dimension of the field increased again. So here you have index of alpha divides period of alpha cube, meaning d equals 3. So these are like some of the known results. Of course, it's like not all of the known cases. And this like period index problem for bar group has been like a long-standing open problem. Yeah, and then like this talk, I will like do a more generalized period index problem for higher degree Galois cohomology groups. As we have already seen, like the bar group is torsion. And following Cuttle, we want to generalize this like M torsion part of a bar group to a high degree version of it. Here the coefficient is mu m, but we twist it to the n-1 power. So here by twisting, we meant the Galois action can be different. And I can be bigger than 2. So like Kato is saying, like we can sort of view as this as an analog of like higher degree bar group. And so like in this talk, like for simplicity, we will be focusing on the case when M is a prime number. And when we think about like classes, we take non-trivial classes alpha in H1F with coefficient mu m twist to n-1 power. So in this case, we always have period alpha equals L. And we can similarly define the index of alpha as the GCD of the degrees E over F, such that alpha E alpha splits over E inside HI of E. So we also know a fact generalizing Barr's classical result. We will have index of alpha divides L to the D. Here D also depends on alpha. And yeah, and so this like also raises the question as an analog of the classical period index problem. If we are given this fixed I, a field F and a prime L, whether there exists an exponent D such that the index of alpha divides L to the D for like all alpha in the higher degree Galois cohomology group. And if so, is there a bound? Recently, this was studied by Harbater, Hartman, and Krashen. They studied for a semi-global field F. Using the field patching technique. And my work relaxed their assumption on the field. But before stating my results, I will first introduce the field definitions to make everything like more precise. So we define a Hensel semi-global field as a one variable function field. Over an excellent Henselian discretely valued field. So like here, the assumption of like excellence is actually like looks like a very strong condition, but it's actually very mild. Most of the rings we have encountered are probably like excellent, and therefore most of the objects in algebraic geometry, as like finite type stuff or whatever, they are all like excellent. So this is not a strong condition. One example of for example, a Henselian DVR will be like a ring of algebraic series over a field little k. So here by algebraic means it satisfies some like algebraic condition. For example, square root of like 1 minus t is algebraic. But like for example, like e to the t is not algebraic. And by completing t like respect to like this uniformizer t, this t hat is the ring of power series. Over this field K. And also in terms of like studying the like generalized period index problem, it turned out to be easier to study a more like a stable bound for like HI of like E with coefficient mu L for all finite extensions E over F. So which motivates the following definition called the stable I splitting dimension. of F at L. We use the notation SSD. This is defined as the minimal degree minimal exponent D such that for any finite extension, field extension E over F, and for any alpha in HI of E, we have index of alpha divides L to the D. So this is like a more uniform bound. If we can find a bound for this SSD, then this automatically gives us the classical period index bound. Okay, so Harbater, Hartman, and Krashen, they proved the result for the SSD for like a semi-global field. And my work relaxed their assumption on the completeness to like the Henselian case. So here's my main result. So if we have a Hensel semi-global field, meaning that's a Van variable function field with Henselian over Henselian discrete value field, let's suppose this Henselian discrete value field has residue field little k, and this characteristic of the little k is not L, then I've shown that SSD of F is bounded by SSD of the residue field K and SSD of the Van variable function field over little k plus some correction terms, which is 2 when L is odd, and when L is like 2, this correction term is 3. And also like this result can also be generalized to non-prime like coefficients. If we can decompose this M into this like prime factorization of like L1 to the A1 all the way to Ln to the An, SSD of F at M is bounded by the maximal of SSD of like one of the Li's. Okay. Yeah, so this result is a iterative bound depending on the SSD of the residue field and the rational function field over that. So these two terms comes from the underlying geometry of the model we pick for the Hensel semi-global field, and I'll introduce that later. So the ingredients in the proof. So first we have a like patching result for étale algebras. In the Hensel semi-global setting. And also we need a like local global principle. For the higher degree Galois cohomology group. So first, for patching, this field patching technique was invented by Harbater and Hartman in their 2010 paper called patching over fields. The idea is that if you want to give a algebraic structure over a base field F, this is the same as to give such a structure over a suitable collection of overfields. And one of the easiest example we can think of is like just do the easiest algebraic structure, which is like vector space. So if we start with a base field, with two overfields and which admits a common overfield F naught. So if we start with a like vector space over F1 and the vector space over F2 of the same dimension, so let's suppose after base changing to like F naught, they are isomorphic, and we fix this isomorphism phi. Then the question is does there exist a vector space over F such that when this vector space V base change to the field Fi is isomorphic to the vector spaces Vi when I is 1 and 2, and also make this whole diagram commute, meaning like we want this vector space induce the same isomorphism phi. So note that here fixing this phi is very important. Otherwise, like any vector spaces of the same dimension will be isomorphic, and this question will not be interesting at all. Okay. Yeah, such a question is called a patching problem. And we say if a solution, like if V exists, we call V is a solution to the patching problem. Use the notation V1, V2, colon phi, indicating that we want to fix this phi. So then I'll like so instead of like giving very technical definitions, I want to like use this slightly easier example to like give a sense of like what kind of fields can satisfy patching. For example, we can take this T to be the like ring of power series, and we take curly X as a projective T line, and suppose has the closed fiber X, which is just like curly X base change to K. So the picture of this this curve will be thickening at the closed fiber, and the function field of curly X, this F hat, is this like one variable function field of the Laurent series field over K. And this is a example of a semi-global field. Then for constructing the overfields, we need to like do it from the geometry of the closed fiber. So we first pick a point X, and in this case, to be like simple, we can take the point at the origin. And we can define the ring RP hat as the complete local ring at the point P. And in this case, this will be Laurent series this will be power series in two variables. And if you draw the picture of spec of like RP hat, this will be a thickening at the origin. And for other overfields, we can take U to be the affine K line, constructed from just like X taking away the point P. And we define the ring RU hat as the T-adic completion of this ring, where we take F from the like function field, and we require F to be regular along U. And in this case, this ring will be K joint X inverse double bracket T. So to look at this picture, it's gonna be like a pinch down. At the origin. We can define like the fields Fp as fraction field of Rp hat, and the Fu as fraction field of Ru hat. So in our case here, this Fp would just be the Laurent series in two variables. And for Fu, there's no like more explicit description of this ring. And we leave it at this. And for the common overfield F naught, we can, in this case, we can take that to be the like Laurent series over the Laurent series over K. And we call FPs and FUs like this local fields as like patches, and F naught as like a branch field. And such a branch field exists when P lies on the closure of U in general. But in our case, since we are like specifically picking this point P and U, like it's automatically satisfied. Okay. So in Harbiter and Hartman's paper, 2010 paper, they had shown that patching for vector spaces over this quadruple fields F, Fp, Fu, F naught always has a solution. And for like the strategy of their proof is basically to show that there are two properties can be satisfied. One of them is the intersection property. Where you have F equals the intersection of Fp and Fu inside F naught. And the second one is called the factorization property. So it's just saying if you have like a matrix A naught in GL over like F naught invertible, you can factorize that into like the product of a matrix AP over Fp and AU in Fu. So you can write A naught as product of these two. So once we know these two properties, to prove patching for vector spaces holds, it's really just like a few lines to say by like a few arguments using change of basis. But actually like to get to these two like properties, it takes like 30 to 40 pages to prove. And these are called the criterions for patching to hold. And once you prove like patching for vector spaces, you also get patching for more complicated algebraic structures. For example, like central simple algebras, like associative algebras, like étale algebras, for example. And actually, like in general, you can do this patching business for some more complicated curves instead of just a projective P line, like projective T line. And also you can work with more points. You can take a finite collection of points on the closed fiber. And for the patch constructing from affine open sets, you can take any of them inside X, excluding these like collection of points we picked. But like then once you constructed these like overfields, you actually got an inverse limit of fields. And you can show that patching actually holds over there in the more like complicated case. But in this talk, we will be focusing on the four fields case for simplicity. And yeah, so like to get patching for other objects, you basically treat them as like vector spaces with other structures. And in this talk, we will be mostly focusing on étale algebras. So yeah, then I have like maybe the last bit of like notation to introduce. But it would be straightforward from like the previous semi-global case. So in our Hensel semi-global case, so we can take T to be the ring of algebraic series. You can take a T curve, curly X, and you can take F to be the function field of this curve. And once you base change this function field to like, oh yeah, so like this ring of algebraic series, you complete that, you get a complete discrete DVR, which is a ring of power series. And you can base change this curve to T hat to get a curve we dealt with before. And for like the function field of X hat, it's basically just base changing F to T hat, and then we take the fraction field. So then for the like local fields, like we define like FPH as the fraction field of the Henselization of this point at the point P, and you define like FUH as the fraction field of the Henselization of the ring F in the function field and the F regular along U. Geometrically, you can think of like Henselization. So like geometrically, like completion is like sort of like thickening, but geometrically, Henselization, you can think of that of like you take the inverse limit of étale neighborhoods of the point P or the open set U. And we call like these two fields Hensel patches. And also one remark is that if we like complete the Hensel patches respect to the ideal on the ring level, like respect to the ideal defining P and U, we can recover the patches. Then this comes my my patching result for étale algebras. So patching for étale algebras would hold for this quadruple fields of like Hensel semi-global fields and Hensel patches. One remark I want to make is that even though previously in the semi-global case and in the complete business, patching is first proven for vector spaces and then got generalized to other algebraic objects. But it's actually like we are not really entirely sure whether patching would hold for vector spaces here, as their original proof doesn't really like generalize, which is like very surprising because one would usually expect like if you have a proof work for complete, that should work for like Henselian. So here we really have to do something different. So once we start with a patching problem for étale algebras in the like Henselian scenario, and we can always lift it up to a patching problem in the complete case. And same for the isomorphism, it's a base change. And by the result of Harbater and Harman, we know that there is a solution L hat over F hat to the like patching problem upstairs. And then we want to like apply a like modified form of Artin approximation. To descend this solution to an étale algebra. L over F. So like let me briefly write down Artin approximation. So if we start with a ring that's excellent Henselian, DVR, and you have a functor from the category of T algebras to sets that is locally of finite presentation. Then the fact that there exists a T hat point of this functor would imply the existence of a T point of the functor. So it's basically saying if you have a formal solution, you can approximate algebraically. And in our proof, once we to apply a chain approximation, of course, we need to check the properties of the functor being locally of finite presentation. And after we got a candidate of this L over F, we handed from Artin approximation, we still need one more step to check L over F is indeed a solution.
You meant probably that it is not equal empty set.
I'm sorry. This is not empty.
Yes,
yeah. Okay. So yeah. So then why do we need patching for algebras here? Because like when we try to like we want to construct local fields over those patches, but once like but usually like fields, the properties of like when you base change field to a bigger field, it's no longer a field. But we can always treat these like local splitting fields as direct summands of étale algebras. And then from there we can use patching to descend to a global splitting field. That's why like we want to consider like patching for étale algebras instead of like for other objects. Okay. And then yeah. So then one more thing, we also need to know a local global principle for Galois cohomology as a last step of our proof. So like the idea of like doing local global principle is that we want to know if a certain property is satisfied locally, whether it's also satisfied globally. One example would be like a Haas-Minkowski theorem. If we have a like quadratic form over Q, and we know Q is isotropic over Q if and only if Q is isotropic over the local fields QP and the real number R. And in general, a lot of objects are classified by Galois cohomology, and one can define a local global map from Galois cohomology. Like mapping to all the like local fields. product of all the local fields. And here, like V ranges from like all the discrete valuations on F. And we say like local global principal holds if the kernel of theta is trivial. And also like if the kernel is non-trivial, we just say local global principal fails. And in this case, it's also interesting to study the size of the kernel, which we also call that Tate-Shafarevich group. So whether local global principal holds or like what's the size of the Tate-Shafarevich group is unknown in general. And like in the case of semi-global fields, and also in my case, Hensel semi-global fields, it suffices to study, using patching suffices to study like local global principal with respect to patches instead of like over those like discrete, like those completions with respect to discrete valuations on F. So which is pretty good because we can just work with like a finite collection of fields and which has like a lot of geometry going on. And yeah, so for applications, it's also usually enough for us to do it over patches or Hensel patches. But in this like theorem, we want to do that for the hard degree case. So when I is bigger than 1, this like result by Harbater-Hartman question in 2004. Sorry, 2014. They show that we have this like local global principal. In this case, like I'll do like the 4 field scenario. So like your local fields are just like 2 local fields. So this map is injective. And in my case, this can be generalized to the Henselian case. So first you have this local maps here. And if you start with a class on the bottom mapping into like 0 over the local fields. And by these natural maps, you have alpha f hat. And here mapping up, you have 0. And by the result of Harbater-Hartman question, we know like local global principal holds. So this is equivalent to the trivial class. And here, by arcing approximation, we can show the map. Phi is injective, which forces alpha to be trivial. And then we also get a like local global principal here. So in the H1 case, because like basically it classifies torsors, which are schemes. To prove this theorem is like a lot easier, but in this case, there's some slightly like extra work to do. Yeah, so then these are all the ingredients. Do I still have a couple of minutes to maybe say a little bit about the proof?
Yeah, for sure. Yeah, maybe
Okay.
2 minutes. But...
Okay, sure. Yeah, so let's first like come back to the theorem. We show this is an iterative bound, which depends on the bound of the residue field and the rational function field over that. The reason we want to compare to these 2 fields is because for the patches, they have like residue fields that are finite separable extensions of the residue field and also the finite extension of the rational function field over the residue field. And we would like to construct splitting fields. Once we take alpha here, we want to construct splitting fields over like FP and FPH and FUH by constructing those over these like residue fields. And there are a lot of like specialization results in étale cohomology that allows us to do that. And we can always treat the splitting field as direct summons of étale algebras. So after we constructed this like local splitting fields, patching for et al. Algebras just allow us to get a candidate for a global splitting field. And from the local global principle, we just proved we can prove this candidate is indeed a global splitting field. So which just gives us like what we want. So yeah, here's the end of the proof and also the end of my talk. Thank you so much for your attention.
Thank you.